Greetings, friends and neighbors. This is Volts for February 12th, 2025. Catching up with enhanced geothermal. I'm your host, David Roberts. Last month, Canary Media hosted two live events in Texas, one in Houston and one in Austin. At both events, I recorded podcasts for you folks. This is the one from Houston. So, back in July 2023, I interviewed Tim Latimer, the CEO of a somewhat obscure startup called Fervo. The company was attempting to transfer the technology advancements made recently in gas fracking over to geothermal energy production. At the time, it had just finished building its first small test plant with funding from Google. Not even 2 years later, a great deal has changed. Fervo built its test plant, in short order brought its drilling costs down by 70%, and started on its first large-scale commercial power plant in Utah. Far from being obscure, Fervo is now an industry darling on the tip of everyone's tongue. The prospect of 24/7, always-on, fully dispatchable, carbon-free power seemed like a dream not long ago, but it is a reality now, and it is set to shake up the entire energy world. What a great time to catch back up with Latimer. We talked about the company's recent achievements, the pipeline in front of it, the hyperscalers that are knocking on its door, and geothermal's bright future. In a rather depressing political and social moment, this is the pick-me-up you need. Hi, everybody. So, a few years ago, well, actually, even more years ago, I think it was 2019, I wrote an article about geothermal power at Vox, where I worked at the time, because I had sort of just started kind of hearing it out of the corner of my ear a couple of times, and I had sort of been vaguely aware of it, and I was just like, well, what's going on with that? And so I went out on what turned into a journey of discovery into, turns out, lots of stuff going on. And one of the companies I came across was Fervo and advanced geothermal. And so then Tim, when he had done, I think, his first sort of like test, came on the podcast, sort of just basically demonstrated that the technology could work, came on the pod. And that was 2 years ago. And lots has happened even since then. So I'm here mostly to catch up. But just to set the stage, maybe you could just start I'm assuming most people in this audience know, but maybe just give us like the minute-long, what is the technology in question here?
Well, I have to say a lot more people know the answer to that question because of your 2019 article. This kind of was maybe an example of how off the radar geothermal is. Sometimes I'm asked now, like, oh, why doesn't anybody talk about geothermal? Or alternatively, I'm asked like, what's all the hype around geothermal? And I'm like, well, both of those things can't be true. And I always remember the days before you wrote that article in 2019, where I think for the next at least 2 or 3 years, everyone had either never heard of Fervo before or they directly cited your one article on the topic. So I appreciate you for putting a spotlight on it. And I do think we're part of the conversation now a lot. So like, everybody should listen to David's podcast and read all the articles he writes because...
And subscribe.
You can find out what the trends are 6 years ahead of schedule. So... It's been a while, but for those who still don't know, one, go read David's article on it, but geothermal is a way to get energy, and that can be heat, that can be heat that we use directly, or it can be heat that we then convert to electricity. And it's an energy resource that's been around as electricity generation for over 100 years. The first geothermal power plant came online in Italy over 100 years ago. By the way, sitting 5 feet away from me is Ann Robertson-Tate, who's run Geothermex for a couple of decades. And so I'm way more nervous about getting anything wrong about geothermal than I normally am. So if y'all hear a loud woman proclaiming that I'm wrong about something, You know who it is, but thank you. She said she's going to be tame. But that first plant came online over 100 years ago, and basically all geothermal power works the same way. There's heat in the ground, and you figure out a way to get that heat moved up in a way where you can spin a turbine. And historically, we've only really had the drilling technology to make that work if you're sitting on top of really special geologic hotspots. So Italy was first, but people famously, Iceland gets most of its energy from geothermal, Northern California, New Zealand, Kenya. There's countries all over the world that get it, but they all face these characteristics where you can make power from it by producing steam or hot water, spinning a turbine with it to generate electricity. But historically, it's been limited to these specific hotspots. I'm sure you're going to ask us what Fervo does in the future, but generally, the basic concept of what Fervo does is that geothermal has all the things you want in an energy resource. It's 24/7, it's carbon-free, it's quick to build, it's proven tech, but historically, it has only worked when you're sitting on top of one of these hotspots. And so there's been R&D initiatives for a long, long time to say, what can we do with drilling technology, stimulation technology, fracturing technology, you name it, to try to get geothermal to work in more places? And that's what Fervo does. But that's the basic concept is, the earth is hot. We can use that heat for something. One of those things we can use it for is to generate electricity.
And just to toot Tim's home a little more, the big advance here is that Tim has taken fracking technology borrowed from the natural gas industry. And so now he can go down and create fissures underground, which then he can circulate water through and it heats up. So you don't have to find fissures anymore. You can make them, which means you can do it maybe not anywhere, but a lot more places than you used to be able to do it. So it's a really cool story. But back when I talked to you, you were just planning on building basically your first actual bona fide power plant for Google. That was 2 years ago. You built the plant. You came out with a white paper about the results. It was pretty eye-popping. Why don't you tell us what you guys figured out building your first plant?
Yeah, so even though EGS, enhanced geothermal systems, has been something that had been worked on since the 1970s. It was Los Alamos National Labs and the Department of Energy that first kind of put the research dollars into this and learned a lot of really interesting things. And there's been projects in Japan and France and Finland and all over the world moving forward, but most of them had fallen short of the technical results that you really needed to prove out commercial viability. And a lot of that came down to flow rate. So it's very expensive to drill. And if you're going to drill, you need to make sure you're getting a high energy output per well that you drill. And so one of the things we set out is a bunch of different targets in terms of power output per well. And by the way, for the scope of some of this project, what we did is we found a geothermal power plant in northern Nevada that had been producing for about 15 years, but they'd oversized the power plant relative to what the actual field could produce, which is a situation you find all the time in geothermal, because the scary thing about conventional geothermal development is you drill a couple wells and it looks good, you size your power plant, you build it, then you drill a couple wells and oh no, you've got a dry hole. And so this plant found its way in that situation where the plant could produce more power than the amount of geothermal steam that was able to flow to the plant. And so we decided to go out to one of the areas in the southern part of the field where they'd had multiple dry holes using conventional drilling technology. And we did the first kind of Fervo system, which is, as you mentioned, we're borrowing fracking technology from the oil and gas industry. But that actually wasn't new for geothermal. That had been tried before. But the new twist on it that we had was an integration of horizontal drilling into the process. So this project, we drilled about 8,000 feet down, and then through Granite, we were able to turn the bit horizontally and drill 3,000 feet plus horizontally. We put two wells next to each other, parallel, at that 8,000 feet down, and flowed through the fractures from one well to the other. And the key thing that made our geothermal work was when you turn horizontally, you get access to way more hot rock per well that you drill than a vertical well. And so we were able to flow across a much larger system of rock so we could get way higher flow rates, and importantly, they could sustain at the same temperature for a lot longer. So we flow tested that well. We were able to show that it could flow at over 60 liters per second, which at that power plant operational efficiency means that our two well system could produce over 3 megawatts of electricity. And that was more than double what any other enhanced geothermal system technology had done. And it was also 10 times higher than what I would say the average output of prior EGS attempts. And all because we could get more bang for our buck because of the horizontal drilling. And then we were just talking to you about how excited we were about the well test results. The exciting thing for us was a couple months later, we were able to build the pipeline, tie that into the power plant, get that system online, actually producing electrons that went to the grid through part of our partnership with Google. And sort of the second big de-risking thing that project was able to do is in October of last year, we hit 12 months of production, and we were able to maintain the same production temperature from day one all the way through day 365, which is one of the other risks of geothermal is if you don't get a system large enough, it can cool down too quickly. And so in one big demonstration project, we showed that we could get enough bang for your buck in terms of power output per well, and that, everyone always says, well, what if it fails in 20 years? And I was like, well, in 20 years, we'll have de-risked that. But right now, it's just been 1 year. But 1 year of completely flat, stellar production and output is a hugely de-risking thing for this tech. So that's what we were able to accomplish there. And we consider it to be the first true breakthrough in commercial viability for enhanced geothermal systems.
And you brought down your drilling costs over the course of that by a lot, by a very large number, 70%. How? To somebody like me, drilling is drilling. Like, how does it get 70% cheaper the second or third time you do it?
Yeah, so first and foremost, drilling time is probably the biggest element that goes into the drilling cost. It is incredibly, if you go to visit one of our drilling sites, we have an incredibly sophisticated piece of equipment, a large drilling rig. We have photos of them everywhere. There's dozens of people out there working at any point in time. So each day you're out there is incredibly expensive, like on the order of $100,000 plus. And then there's a lot of equipment that goes into it as well. And so when we drilled our well, oil and gas and geothermal drilling is quite a bit different. Geothermal drilling, we're in higher temperature rock. We're usually targeting granite because that's where it happens to be that most of the high temperature rock is. We're drilling larger holes, and there's 18 other things that make it different from oil and gas drilling. And so when we first started out, I mentioned this to you earlier, we weren't big enough to get the attention of the oil field service companies broadly. So we were just taking off-the-shelf oil and gas drilling tech and trying to shoehorn it into working in this process. And the problem is that you have these amazing innovations that have made drilling in oil and gas really efficient. Like the one I talk about a lot is the polycrystalline diamond cutter bit. So like over 100 years ago, Howard Hughes invented the tricone roller bit, and that made him the richest man in the world. And that technology dominated the oil and gas industry for about 100 years. And then right when I was starting my career a little over a decade ago, you saw the PDC bit leapfrog and become the predominant drilling bit for oil and gas. And that is, rather than rolling bits that crush the rock, you have a fixed cutter bit where the tips of that bit are synthetic diamonds, because diamond is the hardest substance you can get, and that scrapes the rock away. And so that actually was one of the huge unlocks that opened up shale oil and gas. But all of those bits have been designed for soft rock because that's what oil and gas drills through. And we had to adapt it to work for hard rock. So the first time we drilled a horizontal well, it took us 75 days. It took us $13 million to drill that well because it took so long. In the horizontal section, we drilled 3,000 feet, and we broke 13 bits in the span of drilling that 3,000 feet. And a lot of innovation is not sexy. It's not always like you come up with a whiz bang, like it's not like Doc in Back to the Future where you trip in the bathroom and hit your head on the counter and the flux capacitor comes to you in a vision. A lot of times it's just breaking a lot of things and then running a really rigorous program to figure out why did it break, how do you make it better for next time, and how do you improve. And so there wasn't a lot of experience of people using PDC bits in granite before. And this is just one example. I can tell you through every component on the drilling rig where we've improved things. But we started working with the bit suppliers to say, all right, it broke here this time. Can we add some extra support here? Can we make the blades a little bit longer? Can we change where we put the cutters? And what we saw is actually by the time we were drilling our 10th well, we drilled an entire lateral section through solid granite, 5,000 feet, and we only broke one bit instead of 13. And that meant that we were drilling wells in 17 days instead of 75 days. And it was just a lot of new improvements from a bunch of different innovations, a lot of which was come up with by our team and its proprietary Fervo, a lot of which is partnership through great suppliers. And a lot of this is, as somebody who used to be a drilling engineer in the oil and gas industry, it's sort of like you do the whole 25 years of the shale revolution, but we got that version of the textbook that the teachers get, where there's an answer key in the back, because there's a bunch of tools that have been developed for oil and gas drilling over the last 25 years since the first shale well was successful that weren't developed for the hole sizes and the rock type of geothermal. And we don't have to go invent those from scratch. We can just go to the service companies and say, we want one of those, but we want it in this size and work at this temperature. And so our pace of improvement has been tremendous. And so now we're drilling wells in under $4 million when we used to drill them at $13 million.
So you said the thermal level did not drop over the course of a year, which is big, but I think a lot of people A lot of the questions I get when I talk about geothermal to people who are not familiar with it is they think, do you not sort of suck all the heat out of the ground at some point? Is heat a finite thing that you can deplete, or does it regenerate fast enough? Like, what's the story there? What's the balance there?
Yeah, heat does regenerate. If you waited for that heat to regenerate through rock, which rock is not a very good conductor of heat, you would have really, really low output wells. And so we don't really try to meet steady state in terms of the heat of the rock stays constant over time, because then we wouldn't have 3 megawatt wells, or our most recent well test was 10 megawatt wells. It'd be much, much lower than that. And so we think about this more in terms of how do you design a well program where each one of those wells lasts for 30 years or longer. And then what we have is an ability to, as we continue to innovate on the drilling side, we can drill deeper and deeper and deeper into the resource. So you get to where there's virtually an unlimited supply. And so the heat does replenish, not at a rate that's fast enough that it would be sort of like your economic optimum to do it. And so we drill these wells and space them out and try to access a body of rock that means that it can produce at the right temperature for about 30 years. And then the way we think about our long-term asset management is whenever you get a well that starts to, where it's cooled off the rock locally too much, you can decommission it and start producing from other wells that we drill. And so the way we kind of think about this is we like to design our projects so that the wells last for 30 years, but the assets last for centuries. And that's kind of the general idea of how we think about geothermal resource management.
Just out of curiosity, though, and maybe you don't even know this, maybe we should ask a geologist, but like, if you had tapped out the heat to the point that it was no longer economic, and you shut the well down, and you just waited for the heat to build back up, is that like 10 years, 100, 200, 1,000?
In rock conduction, it's probably, like, we got the geologist right here. And the expert geologist says, I called on you, so you get a free pass. It says, so if we run it for 30 years, wait 50, 100 years, and the heat will recover. And actually, there's been concepts here where people have actually talked about rotation farming, like people used to talk about in the...
like your fields replenish, the soil replenish, kind of similar to...
Yeah. And by the way, the general crux of this is that there's so much heat in the earth, and that heat is also continually regenerating. The reason geothermal is considered a renewable energy resource is that heat supply is almost inexhaustible. And I've gotten into debates with people about this in the past and there was a good analysis that a geologist did, and they published it in a Wired article a couple of years ago that I always point them to, where I hear people say, well, the heat depletes locally, so it's not really renewable. Or, there's only so much heat in the earth. And so you do the math on it, and if you were to take, 2024 global human energy consumption and then divide it over the amount of heat in the earth, what you get is that we only have about 17 billion years worth of heat in the earth. And so my response is, okay, fine, it's not renewable, because in the ultimate heat death of the universe, nothing makes it. But most estimates for the sun is that it'll only last for 5 billion more years. So, we're 3 times longer than solar energy.
All right, so you built this test plant for Google. I don't even know if we should call it a test plant. Like, it's pretty big. It's not like it's not a pilot.
Yeah, it's a real plant.
But now you are building, no more demonstration. You're out building a commercial power plant called Cape Station in Utah. So tell us how big that is, and how long is your list of off-takers? How big could you get it before you exhaust your off-takers?
So what we've publicly announced so far through the first 2 phases is 400 megawatts. And we started drilling this project in 2023. And so just some scale, right? We're going from 3 megawatts to 400 megawatts in one jump. If y'all are energy entrepreneurs, almost always, like, I'd say a lot of my board meetings and a lot of people's board meetings are always the question of how big do you do this time and how big do you go for the next one? Right. Everybody has really strong rules of thumb about, don't do more than a 10x scale up or something like that. But I'll tell you, the really nice thing about the scalability of geothermal is, even though our first project was only 3 megawatts, it was 2 wells, an injection well and a production well.
Yeah, it's modular, so it's not like you're building a giant well.
Yeah.
You're just doing well.
Exactly, and so that's what gave us conviction that we could go way bigger for project 2. because it's just a repetition. Other times when you scale up a plant, you have all sorts of scaling factor issues. Okay, if this is 10 times bigger, are my pressure and volume ratio is going to get off, and all sorts of other questions. And with our case, the fact that we're just repeating that base unit of 2 wells over and over again, you don't have those scale-up issues. So we were willing to jump in with both feet and say we're doing a 400 megawatt project.
How many wells is 400 megawatts?
It'll be about 80 wells. In part because, and we've announced this in our first flow test results that we did in our Utah site, we've actually tripled the power output per well compared to our pilot project, because we've gone deeper, hotter, longer laterals. So our pilot project was at 350 degrees Fahrenheit. We're going to 420 degrees Fahrenheit now. Our pilot project was 3,000 foot laterals. We're doing 5,000 foot laterals now. And there's other changes we made, but we've basically been able to take it to where rather than getting 3 megawatts out of a production well, we get 10 now. So the wells are more productive. And so we're going to do 80 total wells. We've already drilled 20 of them. So we're well along our way here. We're going to put the first megawatts on the grid in 2026 from this project, 100 megawatts in 2026, 300 megawatts in 2028. We started power plant construction there. In October, the Biden administration announced that we'd gotten our final NEPA federal permitting action to expand the site all the way up to 2 gigawatts. So I told you earlier, we've only announced 400 megawatts publicly. The 2 gigawatts thing may give you a clue of how we're thinking about expanding that asset.
One other question about the replicability. How many power plants per well, or how many wells per power plant, I guess would be the right way?
So because we're doing directional drilling, we can put a bunch of wells on one pad. And what we found is the most economic way to do this, to actually eliminate pipeline cost and reduce the footprint of the power plant, is build 1 power plant per well pad. And so for phase 1, we're doing a little bit smaller wells. That's what we're on right now. We have 3 well pads of 8 wells each and 3 33 megawatt turbines that sits on each well pad. And we're generating roughly 100 megawatts of power when we commission that plant. Then we're actually going to even longer laterals and even bigger wells for phase 2. And we're going up to 10 wells a pad. And so we're going to do 50 megawatt turbines for phase 2. And to get back to this point on modularity, I think you did a great podcast a couple years ago about learning curves, which I think is the most important possible concept in technology innovation. I don't mean technology innovation like what software people do. I mean technology innovation
real
like what we do. Is learning curves, which you can get a learning curve if you can drive standardization and modularity from unit to unit. Our team did a huge amount of analysis, and we now call these geoblocks because we've worked with our turbine suppliers to give us a standard 50 megawatt turbine generator combo that matches exactly with our 1 well pad output, and we put 1 per well pad. And the idea is that rather than try to get infinite economies of scale by making the turbines bigger forever, we actually get the right balance between shorter iteration cycles for improvement while not sacrificing too much on economies of scale by specifically choosing to do a 50 megawatt power unit. So when we do phase 2 of this, 300 megawatts, we're going to do 6 power blocks over and over and over again and turn it into something that's a lot more of a mass manufacturing type approach that allows you to unlock these learning curves that rely on standardization and short cycle times.
Right. And is there, in terms of depth that you can get to with your current technology, and in terms of lateral feet, is there some limit? Like, you've pushed it out a ways now. Can you push it out further and further? Like, how far lateral can you go before you get lost out there?
A lot farther. We'll find out. We've gone from 3,000 to 5,000 just in the span of the last 2 years. We're going to do 7,500 later this year. To give you some context, the horizontal wells that the oil and gas industry is drilling now, back when I left the oil and gas industry in 2015, we thought it was like the coolest thing that we could do a 5,000 foot lateral. And you talk to people now, and the records are 20, 25,000 feet, 30,000 foot laterals.
In fracking?
Yeah. And here's a crazy thing for you, if you haven't followed the technology space. Where the oil and gas industry's found the limit isn't from a technical limit, but it's because landowners typically don't own land that extends 6 miles across.
Right.
And so, but you get so much efficiencies from having a longer lateral. No joke, what a lot of the oil and gas industry drillers are pioneering right now is what they call horseshoe wells, where they're literally drilled down 5,000 feet in one direction, do a U-turn, and come back 5,000 feet in the other direction. And that's because sometimes you can't put enough landowners together to drill longer. So the technical limits aren't there. For us, we're having to go through this iteration cycle of learning how to drill in granite and learning how to drill at 450 degrees Fahrenheit, which is a different beast from what the oil and gas industry does. But we think we've developed the right technology tools to go to 7,500 feet now. And we're planning on expanding that to 10 to 15,000 feet in the next 2 to 3 years.
Could you horseshoe? Because I remember when I was looking at the geothermal company Ever, which is doing a closed loop thing, which their water circulates just through pipes rather than loose underground. But they were talking about drilling the pipe down and then having laterals kind of going off like a tree kind of thing. Like, is there any reason you couldn't do a lateral out and horseshoe back and another lateral? I mean, is there a limit to the number of laterals?
No, I'd say what we're doing now is because it's economic and it works.
Right.
And so no need to kind of push the technical boundaries when we already have something. I'm also a big believer in, people call the concept deployment-led innovation or learning by doing. When you look at the hard tech companies that have really done transformational things over the span of a couple decades, you never, ever, ever find a company that said, we're going to work on a 20 or 30-year moonshot, and it's going to be all science and R&D for 20 and 30 years, and then we're going to flip a switch and it works. What you find is a company that figures out how to improve and make money every step of the process, because you got to have some flywheel to fund the process. So SpaceX didn't start out with Starlink, and they didn't start out with the gigantic, Starship rocket they're going now. They figured out, how do you make smaller ones and start with more traditional commercial satellites? And then how do you scale up to make larger rockets there? And so the answer to your question is, we're looking at all of those things, and no telling what 10 or 20 years of dedicated geothermal drilling innovation will do to these. But we have a system that works right now, and we're stepping our way into that. And I'll tell you one other big difference from oil and gas to geothermal that actually opens up a whole new wave of innovation possibilities is oil and gas is always limited in the fact that they have to find hydrocarbon-bearing zones to develop their projects. And so you wouldn't do crazy well geometries. Or sometimes people say, well, if you could drill that deep, wouldn't the oil and gas industry have done it by now? Well, if there's not oil deeper, you don't have an economic incentive to do it. And the oil and gas industry is not in the industry to do strange sciencey things.
To show off their...
And geothermal is far different. So when I was drilling in South Texas, the Eagle Ford Shale, a lot of times you only have a pay package there that's 300 feet thick. So nobody's asking the question, how do you go to 15,000 feet or 20,000 feet or something like that? But geothermal is quite a bit different, because generally, the deeper you go, the hotter it gets. And so when we think about what does the industry look like 10 years from now or 20 years from now, we want to drill yesterday's wells at 350 degrees Fahrenheit and 8,000 feet. Today's wells are at 400 degrees and 9,000 feet. The wells we're drilling next year are 450 degrees and 11,000 feet. And the fascinating thing is, because we're not chasing a hydrocarbon package, the fact that we're just chasing heat means that if we improve the technology so we can drill hotter and deeper, it improves our economics. So it's an industry that has a totally different technology curve than oil and gas, because there's actually a technology and financial incentive to figure out how to go deeper. And that's not something that generally the oil and gas industry has had. So I think when you think about what our industry will look like over a 20 or 30-year period, everything you just said about multilaterals or crazy loops or wild designs is in the cards, because it actually doesn't follow the same constraints as oil and gas drilling.
So if you're going to identify, say, the three big trends that are going to bring costs down for Fervo going forward, deeper, farther lateral, are those the main things?
Deeper matters a lot, because if you can go from 400 degrees Fahrenheit to 450 degrees Fahrenheit, you can actually improve your power output by 30%.
Yeah, you get exponential.
Flow. It gets exponentially better. So that'll be a huge thing. We're going to continue to drive drilling costs down. What's fascinating, if you were to take the in-rel CapEx stack for an enhanced geothermal system project from 2 or 3 years ago, before Fervo published our results, what they would have told you is the power plant would have cost you $3,000 a kilowatt, and the drilling would have cost you $30,000 a kilowatt. And so all of the R&D focus was on driving down the drilling costs. And $3,000 a kilowatt is pretty expensive for a power plant, but when it's just the tail wagging the dog, there wasn't a lot of R&D focus on it. What we've done now from Fervo's standpoint on drilling innovation, keep in mind, just in the last 2 years, I told you we've tripled the productivity of our wells by dropping the cost by 70%. We've dropped our subsurface costs by an order of magnitude. And so now we're talking about sub $3,000 a kilowatt subsurface costs, actually getting close to sub $2,000 a kilowatt subsurface costs. And so all of a sudden, there's been decades of focus on the drilling side of this equation. And in the span of about 2 years, we've taken the drilling part of the equation from being the prohibitively expensive part to the cheaper part of the operation. So you look at our engineering team, you can tell what we were focused on, because 3 years ago, I think Quinn is here somewhere. Is Quinn here from our team? He may have stepped out, but Quinn was the entirety of our power plant engineering team, a team of one, because it just wasn't a primary focus of ours. And we probably had 20 times as many people on subsurface technical challenges. We now have more engineers on the power plant side focusing on cost saving opportunities than we do on the subsurface side, because all of a sudden it's the bigger part of the cap stack.
Let me ask about that, because if there's one thing that seems like it's been standardized over time, it's a steam turbine. Like, what is there something unique about these steam turbines that is bespoke to geothermal?
So there's some geothermal that uses steam turbines, particularly the really high temperature resources. If you're in one of the conventional, New Zealand or Northern California plays, but almost all of the growth in the U.S. geothermal market over the last 10 or 20 years has been in organic Rankine cycle turbines, which isn't a new tech. Right. It's also, Rankine was in the 1800s, I think. So it's not like it's new, but it's only just now finding like mass market adoption. And the key is you can get higher efficiencies at lower temperature. And so until ORC units got rolled out, the cutoff for your minimum viable temperature for geothermal might have been 500F or 550F or something like that, because it just wasn't efficient enough to run a steam turbine there. So we do organic Rankine cycle systems. And even though there's been hundreds of gigawatts or thousands of gigawatts of steam turbines built over the years, collectively, there's only been 4,000 megawatts total of organic Rankine cycle turbines. So it's still a technology that's not that far down its learning curve. And so you think about the one project we're doing in Utah right now is going to be 10% of the global market for ORCs just in one project. And if you look at Fervo's growth targets, we're going to get there very, very quickly. And so there's different technology innovation tools. We're pretty wedded to using organic Rankine cycle turbines. I'll tell you one of the keys for this.
Even if you're deeper and getting hotter?
Yes. And I can tell you the reason. There's two reasons for it. One is financial. Geothermal brine can have different things in it. And exposing your steam turbine and all of your equipment at the surface to that geothermal brine can lead to crazy corrosion and scale issues. I'd say the second thing is it is important to Fervo as a company, and I think the geothermal industry, to be zero emission. And a steam turbine is not necessarily zero emission, because if there's CO2 or other things in the geothermal brine, it can actually lead to emissions. And I'm a little tired of the industry having to explain, like, we're a tiny enough industry as it is, and having to explain different stories to different. It's probably confusing whenever you start talking to it, because is it low emission or no emission? Do we use some water or no water? There's just all these questions. And if you use a air-cooled system that is organic Rankine cycle, because all we do with the geothermal brine, bring it up, we run it through a heat exchanger, we pump it back down. It's a no emission technology. And I think as we scale, it's going to be more and more important over time to be no emission, not just low emission. And standardizing and driving innovation on a closed loop organic Rankine cycle system with air cooling is a way where you can go and put those power plants anywhere in the world, not worry about the emissions, not worry about the water, and just go. And so we think it's a superior technology. And Fervo is all in on that, because I think the standardization benefits and the environmental benefits of this type of power generation outweigh any potential upsides from using different technology.
And there's lots of innovation headroom still.
There's a lot of innovation headroom.
So before we get beyond the technical stuff, let's talk about drilling deeply. We just visited, some Canary folks and I, earlier today, Quaise, the company Quaise, which is trying to go deep by using millimeter waves. I always want to say lasers. I wish it were lasers. Millimeter waves to literally melt rock. We watched them melt rock in front of us. It's quite mind-blowing. So that's one area of innovation for getting deeper. How are you going to get deeper and deeper?
Yeah. It's a good question. We're excited to follow Quaise's journey. I should say, we at the end of the day are a developer that uses technology to further our progress. And so nothing would thrill me more than to see Quaise have a breakthrough in technology, and we would immediately be a huge customer of theirs. We think for the next 5 to 10 years, while there's other alternative technologies that are trying to kind of scale up to get to higher levels on the technology readiness level, you talk about innovation headroom. I think there's been so little drilling with modern rigs and automation, with PDC bits in a granite environment, that what we've done by cutting our drilling times by 70% in the last 18 months is not close to scraping the bottom of the barrel here. And what we've done now is we consistently are drilling faster than 100 feet per hour. We consistently are having bit lives where we can drill for 2,000 feet, 3,000 feet or longer. And I think we're going to get to a point relatively soon here where we're at 200 feet per hour, 10,000 foot bit life. And when you start hitting those kinds of numbers, going to 15,000 feet or 20,000 feet, which is kind of in our medium-term plan, is imminently doable. And by the way, if you can get down to 20,000 feet, there's enough geothermal resource to power the United States many, many times over. And so we're already in an area where the innovations we've gone that have allowed us to increase the depths of our wells by a few thousand feet just in the span of the 3 years we've been drilling aren't slowing down anytime soon. And we think we're going to be unlocking a market that is ubiquitous in terms of geothermal power generation relatively soon, just on the trajectory we're on right now.
Okay, so let's talk about applications, although I guess in our current context, power demand is so crazy and rising so fast. What to do with your energy is probably not high on your list of worries, but it seems like data centers are everywhere. Data centers are on everyone's mind. You know, this is a vexing thing for the clean energy folks because these data centers need enormous amounts of always on steady power, which is very challenging with existing zero carbon technologies. Although, you know, there's white papers out there on how to do this with solar and storage, mini grids. But it's a vexing problem, and this seems to fit hand in glove with those needs. So do you have data centers knocking down your door already? Are they on their way to Utah to build next to you? What's your relationship right now with data centers?
Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who change majors or careers after hearing episodes of Volts. People using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show.
What's your relationship right now with data centers?
Yes. Well, data centers and sort of the leadership in the tech industry is one of the key things that got Fervo started. You know, we already mentioned the partner for us on that very first project we did was Google. And it was because Google, even going back into 2018, launched this 24/7 carbon-free energy initiative, which was focused on total decarbonization of their electricity supply and recognition that even though they're one of the largest buyers of wind and solar in the world, that they needed to complement that with emerging technologies to get all the way to 24/7. And we've been excited to expand that partnership. In the summer of 2024, we announced what we call the Clean Transition Tariff, which is a multi-party agreement between Fervo, Google, and Envy Energy so that we can develop and sell Google 115 megawatts of power through a new project that we're going to be developing in Nevada as part of that continued partnership. So it's definitely happening. The renaissance, it's cool to be in power again. That's the thing. And when kind of we started this company, actually the number one reason VCs passed on Fervo back in the early days was they just didn't think anybody would want the power, which is quaint to think about today. But the idea is that, you know, you think about 2020, there'd basically been flat power demand growth in the United States for 2 decades.
Which means you add something, you take something else off,
yeah.
Which is a fundamentally different situation than we're in.
It was a zero-sum game. You were also looking at a situation where solar had gotten really cheap, and I think people were just basking in the glow of the success that solar was cheap, and natural gas had gotten really cheap, and I think people were basking in the glow of the success that natural gas had gotten really cheap. And you weren't seeing these ambitious 100% renewable energy targets or 24/7 carbon-free energy targets. So it's kind of like, nobody's going to want the power. You fast forward today, it could not be a different market in the power world. You have many jurisdictions and many companies that have actually committed to not a 10% or a 20% renewable portfolio standard, but 100%. You have things like, we're here in Texas, obviously. Like, I think like most of y'all, I lost power for a week during Winter Storm Uri, and that was not fun. One of the big things for our business is in August of 2020, the state of California had its first rolling blackouts since the old Enron energy crisis 2 decades before. And that spurred the California Public Utility Commission into action to think about how do we round out capacity for reliability. And they took a procurement mandate that included geothermal. And so we were already seeing new demand signals. And then late in 2023, ChatGPT goes viral and everything about the world got turned upside down. And now all of a sudden, there's sort of now 3 phases in the American electricity grid: the 100 years where it was growing exponentially, the 20 years where it was completely flat, and now we're back on the exponential curve again. And the relationship, we think a lot of our business is going to be driven in the near term by this data center demand. And I can tell you the way these conversations have gone is 5 years ago, we talked to somebody and they wanted 20 megawatts of power somewhere and they didn't really care what it was. And you talked to them about siting and they were like, well, we need to go where the fiber's good. We need to go where there's a workforce. We need to go where you have access to water for cooling. Utah doesn't check the box. So like, have a nice life. And that was the answer we got, because energy access was probably one of 15 different criteria for siting a data center. And now all of those customers are coming back and say, hey, we'll come to you. Can you do a gigawatt for us now? Not just 20 megawatts. And what you've seen is the market has shifted enough where energy access, I think, went from being, middle of a list of 15 priorities for data center siting to probably number 1. And I've asked some of our folks, like, well, you told us it was a non-starter 2 years ago, and here we are. And it's like, okay, it turns out all the other problems are solvable, and energy, access to new energy, reliable energy is sort of the gating factor there. And so, you ask 10 people, you'll get 11 different opinions on how much power demand AI is going to drive over the next 5 to 10 years. The answer is it's positive, it's large, it's huge, and it's a totally different set of customers and strain on growth of the U.S. electric grid than anything we've ever experienced before.
Yeah, and I'll just throw in here, within 10 years, we're going to be well into electrifying transportation world over, electrifying buildings, heating and cooling world over, electrifying industry world over. So the rise in energy and electricity demand, there's in no danger of being any kind of blip or short-term fad. That's the rest of our lives.
And I will say, I'm glad you pointed that out, because I do think AI is the shiny object. So that's what gets all the attention. But let's not forget, even before the ChatGPT moment, demand forecasts were rising again, because we're onshoring manufacturing, we're electrifying buildings, EVs are coming onto the grid, there's new economic development. And really what you had is a system that was used to growing like this, where, like you said, 1 in, 1 out, that's it. It's not the employees, the supply chains. Nobody was set up to bend like this. We were already bending like this. And then we had a new, from those things, industrialization, clean energy, onshoring manufacturing, electric vehicles. And then you had one more thing to it. And that was the thing that really got people to realize it's a totally different era.
So before I leave the data center thing, they want a gigawatt from you. So you've got this 8-well pad that is producing how much, you said? 50?
That's 30 megawatts now.
30 megawatts. And
we're working on a 10-well pad that does.
Yeah, so I'm trying to help us envision what a gigawatt of your geothermal looks like. That's a big chunk of Utah desert, is it not?
So yes and no. Is it a sizable industrial complex? Yes. Is it a smaller footprint than any other way you're going to get that level of energy from a surface disturbance standpoint? Yes. And so if you come out to our site, and by the way, happy to take you out to our site anytime. It's a fun thing. What we have is these 8-well pads that we stack up one, and then we put another one a little bit to the north and another one a little bit to the north, and we build the turbine generators right off the pads. And so we basically just have a line of pads that you can stand and look at. And collectively, just to give you some sense of scale, that 400 megawatts, when we bring it online and when we bring in the last phase online in 2028, will be over 10% of Utah's power generation. Oh. And we're going to be able to do that within a few square mile area at one spot in the center of the state. So is it big? Yes. Is it big relative to the power output and economic value that it brings to the grid? No. And I think that's one of the other features that's very powerful about geothermal is it's compact from a land use standpoint.
Certainly more so than solar, but not as much as nuclear, right? I mean, nuclear has a problem of being mostly imaginary, but if it were real, it would be smaller, right?
It is difficult to compare our actual project results to imaginary project results, but to be a little less flippant about it, nuclear is also a very energy-dense area. I think there's a renaissance going on in nuclear right now, which I think is very encouraging for the country too. I think when you look at things like the security and standoff requirements of nuclear plants and the footprint of mining that goes into it and other factors, it's not too dissimilar. I'm sure that an endless number of academics have published endless numbers of papers on these that show, directionally, I'd say they're in the same ballpark. They're better than a lot of other energy resources. If somebody wants to really duke it out with me and fight that nuclear is slightly more land compact, I'll concede. Okay. But we both have attributes that are very attractive from an environmental impact standpoint.
Right. So practically speaking, in the short term, the competition to power data centers, your competitor is natural gas. Like if you were a cynic, right? You're watching a lot of big companies with a lot of very lofty clean energy goals run up against the limits, and you wonder, well, which is going to give, the hunger for more data centers or the clean energy target? And, I'm guessing the clean energy target. And gas is cheap. It's right there. It's right at hand. It's easy to build. Utilities know it. Lawmakers love it, et cetera, et cetera. So maybe flatly, how do your current costs of your current Utah plant compare to natural gas?
It's difficult to compare directly to natural gas for a couple of reasons. One is we don't have fuel cost. Right. So you have to take a view on what are the long-term prices of natural gas there. And you also have we have different regulatory risks and exposures and things like that. I can tell you right now, we are generally at a point, and I'm happy to discuss the specific CapEx numbers because we actually published this in our technology day that we hosted here in Houston in September. We are building these projects at around $6,000 a kilowatt right now, which on a CapEx basis is significantly more expensive than what you get from a new combined cycle gas plant. Although I'll say our costs are going in different directions because we're dropping our costs down pretty dramatically. What you're seeing is the supply chain for natural gas power generation isn't used to a huge call on demand like this as well. And so you're actually seeing costs go in the opposite direction for there. So the gap is just closing naturally. But we also on that tech day published where we think our costs are going, which is at the span of 2 or 3 projects, we think we can drop costs below $3,000 a kilowatt. And I think we're going to do that for the reasons I talked about: standardize the power plant, move into a mass manufacturing mentality, dropping drilling costs and drilling hotter wells. And at $3,000 a kilowatt, you can remove all the subsidies, you can remove all the other things that tip the different scales, and just on a CapEx basis, and you take the fact that geothermal doesn't have fuel cost, and I think we have got a better cost than natural gas. And that's even absent, any environmental attributes or any rec factors in, and we're not there today. What we do is that we offer a valuable enough product that our offtake prices, we still make an attractive financial return, which is why we've been able to raise capital and we can find customers who want this. But our vision for geothermal is by 2030, drop that cost to sub $3,000 a kilowatt. And the thing that we think about the energy transition and driving sustainability is you have to offer an end product that is irresistible to your buyer, regardless of the whims of their climate commitments that they may or may not be sticking to. And I think we're on a path to be there in geothermal within the next 5 years.
All right. So I'll just repeat that to put a fine point on it. You think you have a line of sight to being cost competitive with natural gas, absent subsidies, absent carbon prices, absent anything else. Pretty cool. So a lot of people don't know this, but there was a national election recently, and things changed a bit.
I need to get my beer for this.
I know. I think for wind and solar, for dim-colored energy, this is obviously dire. No one knows how dire or exactly what kind of dire. No one knows anything yet. But as I was thinking about this, you seem like, maybe alone among all of Americans, you seem like you're really well positioned. Like this could actually be quite good for you, because I think there's still going to be some impetus for decarbonization. There's still going to be some, and I don't think administrations or state governments are going to want to look like they're just shutting the whole thing down, right? So they're going to favor the non-renewable, clean things, which involves a lot of nonsense, a lot of CCS, a lot of hydrogen, but it also involves geothermal. So I would just wonder, like, the first time I talked to you, I remember years ago, you were like, our problem is not that anyone hates us, it's that no one knows we exist, right? It's that no one knows about us. Now people know about you. As far as I can tell, still no one hates you. Do you feel like you're like this, the new political landscape is advantageous to you, or?
Yeah, in fact, when I told you that years ago, I probably used the same joke that I now use like every time I talk. So I apologize to anybody in the room who's ever heard me talk before. But the thing we find with geothermal is it used to be bipartisan in DC in the sense that neither party knew what it was. And we have, I think, fairly deftly navigated through multiple different administrations, through a huge shift in energy policy priorities, becoming both known and bipartisan. And there's concrete examples of that. One of my favorite, if you look at the new Senate, the chair of the Senate...
Do I have to?
Yes, you have to. The chair of the Senate Energy and Natural Resources Committee is Senator Mike Lee from Utah, a very proud and principled conservative that will tell you that is probably one of the most outspoken people in the Senate in terms of his diehard conservative principles. The ranking member is Senator Martin Heinrich from New Mexico, who is very proud of his progressive bona fides and proud to tell everybody that. You look at where is there common ground for those two people to overlap between the ranking member and the chair of the Senate Energy and Natural Committee and Energy and Natural Resources Committee. I can tell you where it is. Sponsorship of the GEO Act that they both co-sponsored in 2024 to drive more incentives and streamline permitting for geothermal. And so what we find is that there's a lot to like on both sides of the aisle for what geothermal can provide. It's carbon-free energy that employs people from the oil and gas workforce. So it's a just transition workforce story, which is fantastic. It's a climate change story, which is fantastic. You know what else it is? It uses uniquely American innovation. Domestic
extremely American energy.
The drilling sector, which is really exciting. And it's baseload, which is the thing that a lot of, has become. I think somebody did a quote looking at Secretary Burgum's confirmation hearing, and I think there was like 100 mentions of the word baseload because that's what people are thinking about right now. How do you get that reliability? So we find that bipartisan line, and we think it's an area that we will make significant progress in energy access and climate over the next 4 years, and where there may not be that many other opportunities for compromise between the Democratic leadership and the Trump administration. And to kind of drive this point home on a little bit more of a personal level, soon to be Secretary Chris Wright, who just got voted out of the Senate E&R committee 15-5, several Democrat votes. So he has bipartisan support, invested in Fervo through his company Liberty Energy in 2022 and has been a board observer of ours. And so I know a lot of folks on the Democrat side are very antsy about him because he's outspoken on his views on climate. But in his whole hearing, he was unabashed that he's very excited about geothermal and moving forward. So I certainly see this is going to be one of those areas where we're going to have bipartisan support through the next 4 years to make significant progress on climate and energy access. And yeah, I hope to keep it that way.
What happened to the GEO Act? What's the status?
The GEO Act got taken wholesale into EPRA. So that was exciting. It got very close to passing. And then when EPRA fell apart at the end of the last Congress, went back to the drawing board. But there's many provisions in there that fix some long-standing redundancies of geothermal permitting that would really accelerate project development. And we, if there is an opening for a bipartisan compromise on permit reform in 2025, I think geothermal will be included in it. We were a little sad to see that the big compromise bill fell apart right at the end of the last Congress, because I actually don't know if we're going to get a window for a bipartisan compromise on permitting ever again. Yeah. So we'll see what happens.
But that's not a must-have for you. That's a you'd like to have it.
We have certainly managed to get projects through the federal permitting process already. I mentioned earlier our project in Utah is already permitted to expand up to 2 gigawatts. It took us about 3 years to go through the federal permitting process on that. So not as fast as it could be, but not something that is an absolute project killer. The other thing where I think there's alignment both on the outgoing Biden administration and the incoming Trump administration is there's a lot of things that can be done administratively to streamline permitting. And one of the final actions of the outgoing Biden administration was actually pushing through administrative categorical exclusions for geothermal permitting that don't require new laws to be passed, because that was a priority. Developing clean American energy on federal lands was a priority of the Biden administration. And so that was one of the final acts that's actually already made a huge difference in our business. And we do not expect the Trump administration we don't expect them to be bashful on trying to push further permit reforms. So I don't think that progress is going to be walked back.
Got it. If you think about your experience, so you came out of the oil and gas industry and started this thing. So you have been a dude with a pitch deck and a gleam in his eye.
That's all it was in the beginning?
You've been a technology developer, innovator. You've been a first of a kinder. Now you've been a pilot plant. Now you're moving into commercial enterprise. Just how is your head still on straight? It's wild how rapidly you've accelerated through all these phases, and it seems to be like the plane seems to be holding together, and you seem to have your zen about you. What's your secret, Tim? How do you?
Thank you. Every day isn't that zen. But we make it through. It is fascinating. I'll tell you a couple things that I'm proud of in terms of the culture that's been created at Fervo. One thing we repeat all the time that I think is an important thing to think about from a personal growth standpoint and a company growth standpoint is I'll say this phrase a lot, and it's caught hold in our company, that our goals are so ambitious and we're growing so fast that we have to be willing to totally reinvent ourselves on a quarterly basis if we want to succeed. Because it is true. The things that it takes to go from pitch deck to pilot are different skills than going from pilot to developer. And I can be concrete about this. When you fund a really early stage, pre-seed company, what you're looking for is a market size so massive and a technology leap so huge that the naive entrepreneurs sending you the pitch deck can be wrong about 9 out of the 10 things that they tell you. But as long as they're right about one thing, you still have a business. And that's kind of the idea. That whole move fast and break things and try stuff is shoot for something so big when you're early stage, celebrate failure, move forward with that. And you have to embrace that in your DNA as an early company. I see some of my friends in the room who are project developers here. Project development, you could not imagine a more polar opposite organizational.
You do not want to break things in project development.
And I'll also tell you, it's totally inverse. If you're wrong out of 9 and 10 things in a startup, but you're really right about that one thing, you got a business. If you're right about 9 out of 10 things as a developer, but you forgot a permit, or you didn't have the right contract provisions in your insurance agreement, or you didn't get your interconnection in queue in time, or oops, transformers take 5 years to come around, or you didn't get the right labor agreement put in place. Guess what? You don't get an A for getting 9 out of 10 things right. That's a 0. And project development is completely unforgiving. And I think what we have at Fervo, I have some of my colleagues are here in the room, and it's just the team that I think has been really taking that mentality of personal growth and continuous growth to heart, that it's a lot of the same people who had that wild-eyed, let's move fast and break things and let's shoot for the moon. And as we've learned, we've been beaten slowly into being developers where we don't want to make any mistakes. But if you want to be successful in scaling a company, you got to be willing to go kind of on that journey. And everything's about the people, right? And what we've done is we've been incredibly lucky that every step of the way in Fervo's journey, we've been able to get kind of the best talent to join. I don't know, I feel shameless doing a plug, but we have 20 open positions on the fervoenergy.com careers page right now. So if you think you're the best in the best and you want to join, please think about joining our team. But the reason I stay sane is because we've got a team that has taken the challenge of growing themselves with the company seriously.
Excellent. Well, we have time for a few questions, and I bet people have them. Over there.
Well, thanks to both of you for a great discussion and hearing some things in following this area we haven't heard before. I talked to a couple of your colleagues at the break, and I didn't swab them too hard, but I'll swab you. You talked about scalability. In your blue sky view, to the degree that you're comfortable talking about it, Tim, how do we downscale? Because people are talking about small nuclear reactors that, if everything goes right, are going to take 10 years between permitting and execution. You can fill a pad and drill it out in a year or two. Both direct use and smaller scale electric generation, again, to the degree you're comfortable talking about it. Where do you see the future for that, both in North America and elsewhere? Because we know where the Great Basin is in East Africa and Iceland and Java, Sumatra, and that's going to limit us. But there's a big world out there where heat is going from the mantle to the surface, and we can capture that. Thank you.
Yeah, so I think I heard, how do we scale beyond these hot spots, and also how do we maybe do smaller projects to tackle different market
what's
things?
the kind of smallest viable, is distributed at all? What's the smallest viable project size?
5 or 10 megawatts is probably as small as we'd go. I could say what we've learned through doing these projects is our projects do benefit for economies of scale. There's a reason why we're pushing for multi-100 megawatt projects. And so that's what we're pushing on right now. I can tell you that we are looking to go smaller, and to go smaller, you have to get more value for it, right? Because no one wants to pay more for electricity unless you're getting something there. So when we look to go smaller, that is because, are we looking for a direct heat business that may have a different load? And clean heat is incredibly valuable. And as proud as we are about the conversion efficiencies going from heat to power that we have on our sites, you're still talking about low-grade heat that only has somewhere between a 15 to 20% conversion efficiency. So you can just keep it direct heat. There's a lot more you can do there. So we definitely see that going forward. Fervo is certainly not the only company in the space too. I mean, I think I've been really excited to see the ecosystem around geothermal grow up. I think Bedrock is a company that just announced a $12 million Series A just last week, and they're going after more building, heating, and cooling things. So I think there's things you can do to go smaller. It may not be what Fervo does right away, but there's other companies out there, and it's a big market. Moving beyond the basin and range and the East African Rift and things, it's just a function of drilling costs. If you can drill a 20,000 foot deep well tomorrow for the cost of a 10,000 feet deep well today, you can make that project in the money. And so that's why we're so relentlessly focused on dropping drilling costs, because ultimately we don't see any geology as being a place that's not developable. It's just how ambitious can we get on driving drilling costs down?
So my question is, the comparison was made between geothermal and nuclear and natural gas, and it always is. But my question is a comparison question as well between kind of Fervo geothermal versus traditional geothermal. If on your 8-well pad where you're generating 30 megawatts of power, if Joe Geothermal, the traditional geothermal guy, rocked up and drilled those, their typical 8 wells on that same location, what do you think they would have produced, or what would it have costed, or what, pick your metric. I'm just trying to draw a apples to apples comparison.
Yeah, I think that if you look at the well test results, well, number one, conventional geothermal technology probably wouldn't have gotten much of anything because it's so reliant on natural permeability. But if there were to be, like I mentioned this before, between Los Alamos and really when Fervo started, there's been about 50 different EGS attempts, and the vast majority of them got 5 liters per second to 10 liters per second if they were successful, and many of the projects didn't even get to a flow test. And you compare that to 60 liters per second on our pilot project, and we got to 120 liters per second on our flow test there. So we're at least one order of magnitude more productive than what any prior enhanced geothermal systems attempted been. And that's why in 2025, we're talking about EGS, and it's not on the fringes anymore.
Oh, sorry, man. I got a technical question for you. So I know geothermal is lumped into baseload, which is so hot right now, but was not so hot just a year or two ago when solar was ascendant, and we wanted everything to be very flexible, right? And still in some places, I expect flexibility will be the premium thing and not the baseload. So can you tell us, can you be flexible, and how much with geothermal? Is there a problem with depleting the well or having it, lose
I love this question, and I love the answer.
Yes, is the answer.
Specifically, yes.
So we actually have a technology that we've developed, and actually, I haven't mentioned it a lot, but we've gotten this wonderful partnership with the Department of Energy for the last 8 years since we started Fervo. We expect it to continue under the new administration as well. And one of the things we got was an RPE grant to test the technology we call Fervo Flex. And actually at that pilot in Northern Nevada, I can tell you the last year of production, we just brought it on its base load because as you can imagine, in an offtake agreement that's megawatt hour based, that's your incentive as a developer. But we know where the market's going and we know baseload went from being the thing to being dead to now the phoenix rising from the ashes. But clearly the electric grid of the future is going to be one that's driven by ever increasing levels of variability. So we do think that dispatchability attribute is going to continue to be important. And so what was interesting about Fervo Flex is we basically, through this RPE grant, we're able to test our well system in Nevada to operate in a storage and dispatchability mode. And I think one of the things that's interesting about the way we develop our systems is the fact that there's no permeability for the last 100 years has meant that you can't develop geothermal there. But because it's impermeable, actually gives us an interesting way to do energy storage because the only permeability that ends up in the geothermal reservoir is the fractures that we create. And the surrounding area is actually impermeable. And so what that means is that we operated the mode in a flexible cycle where we shut in our production well and kept pumping down our injection well. And we mimicked specifically sort of 12-hour diurnal cycles of no production, flush production, no production to sort of simulate a solar heavy grid of the future and found that we got really great numbers on round trip efficiency. We were able to actually get much higher max peak output than our steady state operations through that energy storage.
So just to be clear, you're capping the output and you're still pumping water down. So just pressure.
Yes.
The energy is being stored as pressure. Basically.
That's right. And so, I told you it's roughly a 3 megawatt project, right? And what you find is that the pumping of that can take up 500 kilowatts or 700 kilowatts. And so that sort of eats into your output in a normal time. But if you actually can run the system in a mode where you only pump, let's say, for example, during the daytime when there's a lot of solar, you take all of your parasitic load and you become a net energy consumer during the day, and you actually build up so much storage in the reservoir that it'll self-flow even without any injection pumping during the evening. And so we sort of simulated that and showed that we could get really strong round trip efficiencies day to night. Because base load is so hot right now, all of our current agreements, like people just want that power around the clock and that's what's driving things. But when we start talking to our customers about 2030's project delivery, building these inherent energy storage capabilities into the geothermal reservoir is something that's driving increasing interest.
Is this something that's far enough along that you have any sense of your duration, how far out you can push your duration?
Yes. And anybody who wants to read more about this, you can look up, we co-authored a bunch of different papers with Jesse Jenkins and Wilson Ricks from Princeton's Zero Lab.
I did a pod with Wilson Ricks on this very question.
You can listen to the pod, which I think is in true Volts fashion, an hour plus long deep dive. You can also read the papers, which I think there's 200 plus pages of how this works. It was a great thing because we looked at reservoir simulation results and we asked the question of, for grids at different levels of solar penetration, to simulate today's grid or a grid 5 years from now or 10 years from now or California versus the national grid, what was the optimum cycle time? We usually found a diurnal cycle time was best. And with the field data we've collected, for sure, we can hit, an 8 or 12 hour storage time. We have not yet kind of pushed the limits on, can you do multi-100 hour energy storage? But
like what happened if you just capped it and kept pumping and pumping and pumping? Like is something going to blow up or pop off or what?
Nothing's going to blow up. It would be completely dependent on the reservoir. I say impermeable. Impermeable is not really it's a meaningless word. Nothing is impermeable.
Right.
Things are just more
Right.
or less permeable. And what you find is even as you pressure up, there's more and more fluid loss. And so there's all kinds of things that are reservoir dependent and system dependent that would shift performance and round trip efficiency. But we've done some tests where, for example, we'll pressure up wells and then we'll go off and do other operations on other wells and come back. And a month after we've worked on the wells, there's still pressure in the system. And so it's completely formation and reservoir dependent, but it certainly has the opportunity to be a multi-day storage system.
Interesting. Well, that is all the time we got. I'm being told to wrap up. So thank you all so much for coming. Thank you, Tim, for all your work. Thanks for Fervo. Thank you for listening to Volts.
It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.